Anomaly detection in time series data. Welcome to this practical introduction. Today we will learn about finding unusual patterns in time series. Detecting anomalies helps in preventing failures, spotting fraud, and much more. Time series are just data points measured over time, like temperatures. Anomaly detection means finding things that do not fit normal behavior. Let us get started and see why this is important. Running the cell now. What is a time series? Time series data are measurements collected in a sequence over time. Some examples are daily stock prices, temperature readings, or website visits. Seeing trends and spotting surprises helps us understand and predict events. An anomaly is something that stands out, like a big spike or an unexpected drop. In real life, anomaly detection is used in industry, health, banking, and more. Running the cell now. It is a good habit to turn off Python warnings when learning. Warnings are Python messages that can clutter our output. Let us import warnings and hide all future warnings for easy reading. Hash always start by suppressing warnings. Import warnings. Import numpy as np. We set the random seed to 42 for reproducibility. Warnings.filter warnings, ignore. Running the cell now. This code snippet sets up the environment for working with time series data by suppressing warnings and fixing the random seed for reproducibility. Although it produces no visible output, this step ensures consistent and clean outputs in later analysis, which is key for reliably spotting trends and anomalies in time series. We need some real data to work with. Let us load a public time series dataset that records ambient temperature readings. This data is from a cooling system, and it actually includes a known equipment failure. We read the CSV file from GitHub, count how many rows and columns it has, and preview the first records. Hash data setup, load a real-world time series dataset, ambient temperature with system failure events. Import pandas as PD. URL equals https://raw.github-content.com/nab/master/data/real known cause/ambient_temperature_system_failure.csv. df equals pd read_csv, URL. Print df.shape. Print df.head 3. Running the cell now. The output shows our dataset has 7,267 rows and 2 columns, a timestamp and a temperature value, capturing hourly readings over time. This setup highlights the essential structure of time series data, sequential measurements, forming the foundation for analyzing trends and detecting anomalies later in the lesson. This loads our temperature data into a data frame called df. We can see the number of rows and some sample records. In this dataset, the temperature value will change over time. Let us prepare the time column so Pandas knows these are actual times, not plain text. This allows us to work with dates easily. Sorting by time ensures our chart and analysis go in the right order. Checking data types helps confirm the column is now a date-time type. Hash convert time column to date time and sort data. df timestamp equals pd to underscore date time, df timestamp. df equals df.sort underscore values, timestamp dot reset underscore index, drop equals true. Print df.dtypes 2. Print df.head 3. Running the cell now. Here, the code converted the timestamp to column to a date time type and sorted the data by time, essential steps for working with time series. Notice the output shows the first 3 rows with hourly timestamps in order and their corresponding numeric values, setting the stage to analyze trends and detect anomalies over time. Now, our timestamps are in the right format and order. This makes future calculations accurate and easier to follow. Seeing the data is the best way to start. Let us make a simple line plot of temperature over time. The plot will show if there are any sudden jumps or drops. Hash plot the temperature data over time. Import matplotlib.pyplot as plt. plt.figure, fig size sad smiley 12:4. plt.plot, df, timestamp, df, value, color equals sky blue. plt.title, ambient temperature over time. plt.xlabel, time. plt.ilabel, temperature. plt.show. Running the cell now. This plot shows the ambient temperature measured over time, with the x-axis representing the timestamp and the y-axis showing temperature values. Notice the overall trend and any sudden spikes or drops, which could indicate anomalies. This visual helps us understand the nature of time series data and sets the stage for detecting meaningful patterns or unexpected events. We can now spot trends, cycles, or outliers by eye. Large spikes or dips could be anomalies or signals of system problems. Summarizing our data gives us a quick overview. We use describe to get the average, minimum, maximum, and more. This helps us define what is a normal for this series. Hash describe the temperature data to find basic statistics. Stats equals df, value, dot describe. Print, stats. Running the cell now. This output summarizes the temperature values over time, showing us key statistics like the average, mean, around 71.2 and the range from about 57.5 to 86.2. Noticing these helps us understand the usual temperature behavior and sets a baseline for spotting anomalies, values that are unusually high or low compared to this typical range. The average and standard deviation are especially useful when looking for anomalies. Before searching for anomalies, we should confirm we have all data. Missing values can confuse anomaly detection methods. We count how many missing entries there are in the temperature column. Hash check for missing temperature values. Missing equals df, value, .isna, .sum. Print, f missing temperature readings, missing. Running the cell now. This output shows that there are 0 missing temperature readings in the dataset, meaning the valued column is complete. This is important in time series analysis because gaps can disrupt trend detection and anomaly spotting. By confirming no missing data, we ensure our subsequent analysis will be more accurate and reliable. If we found missing values, we would need to handle them first. Missing values can be filled or removed, depending on the case. Let us clear out any records with missing temperature, even if the count just showed 0. This makes sure our data is safe for processing. Hash remove any missing values just in case. df equals df.dropner, subset sad smiley value, .reset underscore index, drop equals true. Print, df.shape. Running the cell now. This output shows the shape of the clean time series data, with 7,267 rows and 2 columns. The 2 columns likely represent the time points and their corresponding values, confirming we have a continuous sequence for analysis. This step ensures the data is ready for detecting trends and anomalies without any missing values that could disrupt the patterns. The shape shows us if any rows were dropped. Simple approaches to anomaly detection. The easiest way to find anomalies is with the mean and standard deviation. If a value is far from average, it could be an anomaly. We can mark values that are more than 3 standard deviations from the mean. In real systems, many other methods are possible too. Let us try this simple method first. Running the cell now. Let us find out what is normal using mean and standard deviation. Any temperature more than 3 standard deviations away gets marked as an anomaly. We count how many points are normal and how many are unusual. Hash mark anomalies using the mean and standard deviation rule. Mean equals df, value, .mean. std equals df, value, .std. Threshold equals 3 std. df, anomaly, equals abs, df, value, mean, threshold. Print df anomaly dot value underscore counts. Running the cell now. This output shows the count of rows classified as anomalies based on the simple rule, values more than 3 standard deviations from the mean. Notice there are only 19 anomalies out of 7,267 total points, highlighting how rare extreme values are in this dataset. This confirms our method effectively flags just the most unusual data points as anomalies. Most data points should be normal. A few points will stand out as anomalies, flagged as true. Let us visualize both normal and strange values on our chart. Red dots will show us exactly where the anomalies are found. Hash plot anomalies on the time series chart. plt.figure, fig size sad smiley 12:4. plt.plot, df, timestamp, df, value, label equals temperature, color equals a light gray. plt.scatter, df.loc, df, anomaly, timestamp, df.loc, df, anomaly, value. Color equals red, label equals to anomaly, zorda equals 5. plt.legend. plt.title, temperature with anomalies highlighted. plt.xlabel, time. plt.ilabel, temperature. plt.show. Running the cell now. This plot displays the temperature over time with anomalies highlighted as red dots. Notice how these anomalies stand out far from the main trend, confirming they lie beyond 3 standard deviations from the mean. This simple visualization helps us quickly identify unusual values in the data using the basic statistical method introduced. You can easily see unusual spikes or drops. This visual makes it clear where we need to investigate problems or events. Why use more advanced methods? Simple threshold rules work but might miss gradual changes or complex patterns. Real systems often use rolling averages, machine learning, or deep neural networks. More advanced methods can catch subtle or contextual anomalies. Let us try a moving average approach, often used in real-time systems. Running the cell now. A moving average smooths the series by taking the mean of recent values. This helps the method pay attention to local context, not just overall average. We flag values that are much higher or lower than the recent trend. Hash detect anomalies using moving average and moving standard deviation. Window equals 50 hash adjust as needed. df rolling underscore mean equals df value dot rolling window dot mean. df rolling underscore std equals df value dot rolling window dot std. df anomaly underscore mar equals abs df value df rolling underscore mean 3 asterisk df rolling underscore std. Print df anomaly underscore mar dot value underscore counts. Running the cell now. This output shows how many data points were flagged as anomalies using a moving average and standard deviation method, with only 39 out of 7,267 points detected as anomalous. Notice the large window smooths the data, helping to catch subtle deviations rather than simple thresholds. This demonstrates how advanced, context-aware techniques reduce false alarms while identifying meaningful anomalies. Some anomalies may be found in slightly different locations. This approach adapts better to local changes or trends in the data. Here we overlay the moving average with temperature. Anomalies found using this method are shown in orange. Hash visualize anomalies found by the moving average method. plt.figure, fig size sad smiley 12:4. plt.plot, df, timestamp, df, value, color equals a light gray, label equals temperature. plt.plot, df, timestamp, df, rolling underscore mean, color equals blue, alpha equals 0.7, label equals a moving average. plt.scatter, df.loc, df, anomaly underscore mar, timestamp, df.loc, df, anomaly underscore mar, value. color equals orange, label equals anomaly, MA, Zorda equals 5. plt.legend. plt.title, moving average anomaly detection. plt.xlabel, time. plt.ilabel, temperature. plt.show. Running the cell now. This plot shows how the moving average smooths temperature data, highlighting gradual trends rather than noisy fluctuations. Orange dots mark anomalies where values significantly deviate from the rolling mean, illustrating how this method can detect subtle changes that simple thresholds might miss. Notice how the rolling average line, blue, provides context for identifying these more nuanced anomalies over time. You can compare this chart to the earlier one. Notice how some anomalies are caught or missed compared to the simple global method. Let us experiment by changing the moving average window size. Try entering 25 or 100 when prompted. Smaller windows react quicker to changes, but might catch more noise. Larger windows smooth out the trend more. Let us see how the anomaly results change with a different window. #mini project, try changing the rolling window size. Window_size equals int, input, choose a new window size, like 25, 50, 100. df, roll_mean 2, equals df, value, dot rolling, window_size, dot mean. df, roll_std2, equals df, value, dot rolling, window_size, dot std. df, anomaly_custom, equals abs, df, value, df, roll_mean 2, 3 asterisk df, roll_std2. plt.figure, figsize sad smiley 12 4. plt.plot, df, timestamp, df, value, color equals gray. plt.plot, df, timestamp, df, roll_mean 2, color equals green, alpha equals 0.7. plt.scatter, df.loc, df, anomaly_custom, timestamp, df.loc, df, anomaly_custom, value. C equals a magenta, label equals custom anomaly, Zorda equals 5. plt.legend. plt.title, f moving average window, window_size. plt.show. Running the cell now. This plot shows how changing the rolling window size affects the moving average, green line, and the detection of anomalies, magenta points. Notice the smoother trend with larger windows and how anomalies are identified as points deviating more than 3 standard deviations from the rolling mean. This visual illustrates how moving averages help capture gradual changes and contextual anomalies beyond simple threshold rules. Try a few different numbers and observe how sensitive or smooth the anomaly flags become. This hands-on experiment will help you understand the effect of window size in moving averages. If you find interesting or important anomalies, save them for further checking. Here we write the list of detected anomalies to a new CSV file. #save detected anomalies to a CSV file for review. Anomalies equals df.loc, df, anomaly_custom, timestamp, value. Anomalies.to_CSV, anomalies_detected.csv, index equals false. Print, f saved, anomalies.shape, 0, anomalies to anomalies_detected.csv. Running the cell now. Here, the code identifies and extracts 39 anomalies based on our moving average method and saves them for further analysis. Notice how this step bridges detection with practical use. By reviewing these flag points, we can evaluate if our advanced approach successfully captures subtle changes missed by simple rules. This highlights the value of using rolling averages for real-time anomaly monitoring. You can share this file or use it later to compare with real system events. Being able to save and report findings is important in all data projects. Tips for real-world anomaly detection. Always visualize your data first. Pictures can show things numbers hide. Start simple with averages and gradually try more advanced tools. Adjust your settings, like window size, based on your use case. Be aware of seasonality. Repeating patterns can look like anomalies. Try machine learning methods for complex data if simple tricks fail. Most importantly, talk to a domain expert. They know what matters most. Running the cell now. Recap and next steps. You learn to load, clean, and explore real-world time series data. You practiced both basic and moving average-based anomaly detection. You visualized results and saved findings for reporting. Next, you could apply these steps to your own sensor, finance, or web data. For advanced anomaly detection, look up algorithms like isolation forest or LSTM. If you enjoyed this, do not forget to subscribe for more tutorials and hands-on guides. Thank you for learning and practicing with us. Running the cell now.